Hi, I'm Cambridge Yang. I'm presenting our paper, Simplifying Dependent Reductions in the Polyhedral Model, co-authored by Eric Atkinson and my supervisor, Michael Carbin. Reduction is a common pattern in various computing tasks. Here's an example reduction that defines the classic example of a prefix sum on the array A, storing the results into B. Reductions are also sometimes called dependent, meaning that the transitive dependencies in the program requires an order of the evaluations of the reductions. Here's an example dependent reduction. You may pause the video to see that to compute bi, one needs to compute bi minus 1, and therefore they are called dependent reductions. Furthermore, it is worth noting that this straightforward specification of this reduction has a quadratic asymptotic complexity. Specifically, the specification requires a loop over n due to the for-all quantifier and another n due to iterating over the prefixes. We also have the alternative specification of prefix sum on the right. You may pause the video now to verify that this is indeed an equivalent specification of the one on the left. Notably, the complexity of this alternative spec is actually linear. We have just decreased, or we call simplified, the complexity of the dependent reduction on the left. In this paper, we propose a formalization of this problem of simplifying dependent reductions and give a heuristic algorithm to help us perform simplifying dependent reductions automatically. Towards that end, we present the following contributions. First, we identify the problem of simplifying dependent reductions, and we present a formalization of the problem as an integer bilinear program. Then, we propose a heuristic algorithm to more efficiently solve the problem. Lastly, we collect a set of 11 algorithms as benchmarks and show the effectiveness of the proposed heuristic algorithm in terms of both complexities and word clock running time. Before getting into the details, I will first talk about where these dependent reductions might occur. We observe that these dependent reductions occur in specifically iterative methods. In iterative methods, the goal is usually to solve an equation x equals gx, and the algorithm proceeds by initializing x0 to some initial value, possibly random, and iteratively evoking the function g to update for the next value of x. Dependent reduction arises for certain g that contains reduction itself. Most notably, this pattern occurs in probabilistic inference. For example, they occur in certain MCMC methods like Gibbs Sampling and Metropolis Hastings. They also occur in belief propagation and gradient-based optimizations such as Newton's methods. Let me show a motivating example. The example is called Gibbs Sampling on two clusters Gaussian mixture model. Let's first suppose that there is a sequence of objects. Each object belongs to one of the two kinds, either blue or orange, with equal probability. On this number line, a blue object is located at -1, and an orange object is located at 1. Suppose that we have a sensor that can make observations of where the object is located at, but not its true color. Unfortunately, our sensor is also not perfect, and each observation it measures is actually noisy. Specifically, it's randomly drawn from a Gaussian with a fixed variance that we know around the true location of the object. This forms a two clusters Gaussian mixture model, and we can write down this probabilistic model as the following. Here, each index I corresponds to each individual object. Each Ci is the true category of the object, and Xi is each observation of the sensor. And the observation is drawn from a Gaussian centered at either -1 or 1, depending on the true category of the object. Now, suppose that we have made several observations to a sequence of such objects. A common task is to make inference on the true category of each object, which are these colors corresponding to the observations. In probabilistic inference terms, we would like to make inference on the distribution of z given all the observations x. One way to accomplish this task is called Gibbs sampling. In Gibbs sampling, we initialize our guesses of the actual category of the objects randomly, and we iteratively update each index of zi by performing what is called a Gibbs sampling step. So here's a specification of Gibbs sampling on two clusters Gaussian mixture model. This specification first defines the following four quantities. C0 is an array indexed by I, with the length of the total number of observations. It represents the counts of the number of points that are currently located at cluster 0, excluding the index I. Similarly, C1 is also an array indexed by I with the length of the total number of observations. It represents the counts of the number of points that are currently located at cluster 1, excluding index I. Next, S0 and S1 are almost the same as C0 and C1, but instead of counting the number of points, they just take the sum of the observations of those points. Lastly, Gibbs sampling samples the next CI with the following three equations. These equations are specific to our two clusters Gaussian mixture model. For this talk, what's really important is that they can be seen as a function whose arguments are the four quantities defined above, and the function just returns. We can now see that this algorithm specification has dependent reductions. In particular, the four quantities contains a total of 8 reductions, and the update function below lets them become dependent reductions. This is similar to our example before with prefix. Same as our optimized prefix sum, we can reduce the complexity of our algorithm by keeping track of the counts and sums incrementally. Let's visualize the optimized algorithm in action. This visualization currently shows the state of the algorithm right before the first Gibbs sampling step. On the top left, we have two histogram plots for the current assignments for the two clusters. The horizontal axis is the value of the observations, and the vertical axes are the counts of the observation values in each histogram bin. The two gray curves are the true Gaussian distributions centered around -1 and 1, respectively. We can see that the histograms are not fit into those true curves because the cluster assignments right now are just randomly initialized. The two color bars at the bottom of the diagram shows the current cluster assignments. The top color bar is just a zoomed-in version of the bottom one. The red arrow highlights which data index the Gibbs sampling step is about to process next. On the top right, we display the four quantities, the counts and the sums, as given by the previous slides. Their values are initialized to the correct values as given by their definitions. In the first Gibbs sampling step, a new cluster assignment is chosen for the first observation. Since the new assignment, which is the blue square on top of the red pointer, is different from the current assignment, orange, the counts and sums are updated by adding or subtracting values accordingly. Then, the red pointer recolors the first observation and moves on to the next index. Again, a new cluster assignment is chosen for the second observation. This time, however, since the new assignment is the same as the old assignment, the counts and sums are left the same. The algorithm repeats the Gibbs sampling step by sweeping through the observations for several passes, and we will see that eventually the cluster assignments visualized by the histogram will approach the true Gaussian distributions. We will now recall some backgrounds. First, we will revisit concepts from the polyhedral model. A polyhedral set is a set of vectors constrained by a system of affine inequalities, optionally parametric. A polyhedral relation describes an affine relation between polyhedral sets. Here is how the dependent prefix sum example is represented in polyhedral model's program representation. A program in this representation consists of a set of statements. Each statement is associated with a polyhedral set domain of the statement. Further, array accesses, both read and write, are assumed to be affine expressions over the iteration vectors. Notably, in our program representation in the paper, reduction is a first-class object. Specifically, the plus equal sign here expresses that the first statement is a reduction with a sum operation. In Polyhedral Model, scheduling is the process of assigning each iteration of each statement a timestamp. Specifically, with affine scheduling, each statement is assigned a scheduling matrix theta, which upon multiplication with an iteration vector will produce the timestamp for that iteration. For this example, here is one possible schedule. Under this schedule, the iteration 00 of statement S1 is assigned the timestamp 00. The iteration 0 of statement S2 is assigned the timestamp 10, and so on and so forth. Timestamps are lexicographically ordered, meaning that their entries are compared from left to right. Here's a diagram illustrating the timeline of the order of evaluations of instances for this example. After obtaining the scheduling matrices, one can perform code generation to generate loop-based code. Here's a potential generated code. You may pause to verify that it indeed matches the computation as given by the polyhedral representation. The key to scheduling is that the resulting schedule must satisfy the prescribed dependencies of the program. In this example, the iteration 3.1 of the statement S1 must happen before iteration 3 of statement S2. The iteration 2.1 of statement S1 must happen before iteration 2 of statement S2. Further, the iteration 2 of the statement S2 must happen before iteration 3.1 of statement S1. And of course, there are many more of these dependencies in the input program. Poche et al. Formulated the scheduling problem as a single integer linear program. For brevity, we will not get into details of the formulation here, but roughly, the algorithm first extracts the dependence relations of the input program and applies Farkas' lemma to constrain the scheduling matrices such that they satisfy all the dependencies of the input program. More details in the paper. Now we review simplifying reductions. Simplifying reductions is the work by Gautam and Rajgopal, published at POPL 2006. One of the contributions of the work is a core transformation called simplification transformation. Let's consider this reduction of prefix sum in our equational representation. We can schedule the reduction and obtain the loop program on the right. The resulting program has a quadratic complexity, as expected. Simplification transformation takes in the reduction and an additional argument called the reuse vector, and it outputs a transformed equational specification. For example, we can feed st with the reuse vector 10 and get the equational program below. And the program below will have a linear complexity once we schedule it. We can feed st with different reuse vectors, for example, -10, and in this case, st will output a program that also has linear complexity. What's more interesting is that now the output program have changed its behavior. So, instead of doing a regular prefix sum from left to right, it first sums all values of a and performs subtraction on b incrementally from the right. It is also possible to use reuse vectors such as 20 or -20, and each reuse vector will produce a distinct program, but all of them would have a decreased complexity. Here are some key takeaways. Simplification transformation is a transformation that takes in a reuse vector and a pointer to a reduction as arguments, and then it outputs a equational program that preserves the semantics but lowers its complexity. st is applicable to multiple reductions that are independent, but because st introduces new dependencies to the program, it cannot handle reductions with existing dependencies, namely the dependent reductions we have presented in the previous slides. We are now ready to present the core contributions of the paper. namely simplifying dependent reductions. Let's consider the example of dependent prefix sum again. We can make an attempt at the STR problem by first trying out to apply simplification transformation out of the box. So why don't we do that? Here, we apply ST with the reuse vector -1, 0, and we obtain the equational program below. Note that this is just applying ST to the reduction at the top, and we get the first two statements at the bottom, then copying the second statement at the top over to the bottom. Unfortunately, this output program has a dependent cycle. For example, observe that to compute bn-1, we need an-1, and to compute an-1, we need bn-2, which then we will need bn-1. This was just a thing that we were just trying to compute. We now make a second attempt by applying ST with the reuse vector 1, 0. This time, the program does not have any dependent cycle, and we successfully schedule the program. You may pause the video now to check that the bottom right loop program is indeed a correct implementation of the original dependent prefix sum, and has a linear complexity. We now formalize the simplifying dependent reductions problem. We will formulate it as an integer bilinear program. The idea is actually quite simple. We will combine the previous works on IOP scheduling and simplifying reductions to obtain a bilinear program that generally solves both the reuse vectors and the affine. Now we illustrate the integer bilinear formulation using the dependent prefix sum example. The first step is to apply ST using a symbolic reuse vector, here written as the vector Ri, Rj. Instead of a particular output program, we now actually get a program that is parametric to these symbolic unknowns, Ri and Rj. Then, we can apply the idea of IOP scheduling on this parametric program. This will give us the desired integer bilinear program. The bilinear program will have all the reuse vectors and scheduler matrices as unknowns, and will constrain these unknowns to satisfy the dependence constraints as well as certain constraints of ST. Finally, we use a linear encoding to encode the complexity of the output program, and use it as the objective of the bilinear formulation. Solving this integer bilinear program will produce the desired solution to the simplifying dependent reductions problem. We refer to the paper for more details on this topic. Unfortunately, there are problems with this integer bilinear program formulation. Specifically, the formulation presents scalability challenges, since even IOP scheduling alone is already a hard problem to solve for sufficiently large input programs. Further, our integer bilinear program is non-convex, and these non-convex problems in general are hard to solve. One contribution of our paper is that we present a heuristic algorithm to practically solve the simplifying dependent reduction problem. The key insight of the heuristic is that we can leverage an existing schedule to the unoptimized original program and use that schedule to guide the process of choosing reuse vectors for ST applications. More specifically, the heuristic attempts to choose the reuse vector that aligns with the existing schedule, and dependencies induced by STs are therefore subsumed by the original dependencies of the input program. It turns out that if we can do this for all the ST applications opportunities, we end up with the optimal program with the minimal complexity. We now illustrate the heuristic algorithm using, again, the dependent prefix sum example. The first step of the algorithm is to augment the program with an additional statement that redirects the values of b. This additional statement S3 can be seen as a finalizer of the computation of b in a reduction S1. Intuitively, if we have a schedule for statement S3, then we get an affine schedule for when each values of bi are fully computed. Next, the heuristic algorithm assumes that an affine schedule of this augmented program is given to the algorithm. Now, the heuristic algorithm performs the following for each ST application opportunity. It first proposes any reuse vector Ri, Rj as a potential candidate reuse vector. It then tests if the reuse vector agrees with the given schedule. It does that by simply doing a multiplication of the schedule matrix theta S3 with the proposed reuse vector. Now, if the first non-zero entry of this matrix vector product is positive, the reuse vector is accepted and it is used for the ST application. Otherwise, if the first non-zero entry of this matrix vector product is negative, the negation of this proposed reuse vector is then used, since we know that this negative vector then must pass this positivity test. More concretely in this example, consider that the heuristic is given the affine schedule shown in the middle, and we know that the projection of the reduction maps ij to I. So, for the reuse vector -1, 0, the result of multiplying theta S3 with the vector -1, 0, 0 is going to be -1, 0, and therefore the first non-zero entry is negative. So the heuristic algorithm decides that this reuse vector does not obey the given affine schedule. On the other hand, for the reuse vector 1, 0, the result of this multiplication is 1, 0. The first non-zero entry is positive, so the heuristic algorithm decides that this reuse vector 1, 0 is indeed valid for the application of ST. Note that this result aligns with our initial 2 attempts at the SDR problem, and it is a test case that shows that our heuristic algorithm is indeed sound. In the paper, we evaluate our heuristic algorithm using a total of 11 benchmarks that contains dependent reductions. The benchmarks are probabilistic inference-related algorithms, and we refer the details of these benchmarks to our paper. Using these benchmarks, we evaluate on 2 ends, the complexity reduction and the improvement in wall clock time, before and after simplifying those dependent reductions. In summary of the results of our evaluation, our heuristic algorithm is able to obtain optimal complexity for all 11 benchmarks, same as if we have solved the simplifying dependent reduction by linear formulation optimally. We collect the typical real application parameter sizes for our benchmarks, and evaluate wall clock times improvements using those parameter sizes. We observe speedups from 1.1x improvement up to 1,000,000 times improvement, with a median of 37 times improvement. This is very much expected, since for these inference algorithms, complexity improvement dominates other constant factors. In conclusion, in this work, we identified the simplifying dependent reductions problem and gave a bilinear program formulation to the problem. We provide a heuristic algorithm that can solve the simplifying dependent reductions problem efficiently and practically, and we obtain good empirical results. Above all, we believe that we have identified a general-purpose optimization opportunity that can be leveraged by an optimizing compiler. It uncovers a promising use case of incorporating our technique into compilers for probabilistic programming systems to move up the abstraction level further and to reduce the programming labor under such systems. We would like to especially thank all who helped along the way this work is developed. This talk would have been possible without all your help and efforts. Thank you for watching, and if you're interested, please check out our full paper for more details.